Imagine trying to perfectly position a tiny, spinning top at the very beginning of its rotation, before it even begins to wobble. In quantum computing, we face a similar challenge with qubits. How do we reliably put them into a specific starting state? This initial setup is crucial for any quantum calculation to work correctly. Yes, radio frequency or RF pulses are indeed a primary and highly effective method for setting a qubit's initial state. These precisely engineered electromagnetic waves are used to manipulate a qubit, coercing it into its desired ground or excited state, or even a superposition, which is a blend of both. This controlled initialization is a foundational step, without which reliable quantum operations would be impossible. The underlying principle here relies on the qubit's energy levels and the phenomenon of quantum resonance. A qubit, in its simplest form, can be thought of as a two-level system. One level represents the zero state, and the other represents the one state. The energy difference between these two states corresponds to a very specific frequency. When an RF pulse is applied at this exact resonant frequency, the qubit absorbs the energy and transitions between its states. The duration and amplitude of the RF pulse determine the extent of this transition, allowing for fine-grained control over the qubit's final state, much like tuning a radio to a specific station. To practically initialize a qubit, particularly to its ground state, the zero state, a common technique involves using a process called cooling. This can be achieved through techniques like dilution refrigeration, which lowers the system's temperature to mere thousandths of a degree above absolute zero. At these extremely low temperatures, the qubit naturally sheds energy and settles into its lowest energy state, which is conventionally defined as the zero state. Once in the zero state, subsequent RF pulses, often called pi pulses or rotation pulses, can then accurately rotate the qubit to any desired superposition state or directly to the one state, laying the groundwork for complex quantum algorithms. This precise manipulation is not just theoretical. It is a daily reality in superconducting qubit platforms, which are currently at the forefront of quantum computing development. The ability to perform high-fidelity single qubit rotations using tailored microwave pulses is a testament to the sophisticated engineering involved. These pulses are typically in the gigahertz range, similar to the frequencies used in modern Wi-Fi or cellular networks, but delivered with exquisite precision and control over their duration, phase, and amplitude. The accurate initialization of qubits using RF pulses ensures that every quantum computation begins from a known and reproducible starting point. This foundational control allows researchers and engineers to construct reliable quantum circuits, perform complex operations, and ultimately extract meaningful results from the fragile quantum world. Mastering this initial step is truly the first ripple in creating powerful quantum algorithms.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.